Section 4.4, oxidation reduction reactions. So now we're going to look at the third type of chemical reaction, which is called oxidation reduction. It is often abbreviated as redox. Okay, so these are redox reactions. Redox reactions often involve an exchange of energy with the surroundings, a large exchange of energy. So redox reactions are often used in fuel cells or batteries, applications that require large amounts of energy. So the idea here is the redox reaction is the case where electrons, so it could just be one electron or more than one electron, are transferred from the reducing agent to the oxidizing agent. So let me show you a physical depiction of this. Imagine that we have a silver ion and we have a lithium atom. And these two species in some method or some way are close to each other. They're within some small distance of each other. Essentially what will happen is the silver ion will pull an electron from the lithium atom. Okay, it pulls an electron off of the lithium atom. Now the electron has a negative charge, and the silver ion has a positive charge. So what happens when you add an electron to something that has a positive charge? The negative charge neutralizes the positive charge. So now this becomes a silver atom, and the lithium has lost an electron, so it now has a positive charge. Let me go through with you the arithmetic of the electrons and protons and charges. A silver atom, silver is element number 47. Now, a neutral silver atom has 47 protons. Remember, the protons are in the nucleus of the atom, and it also has 47 electrons, 47 negative charges. So that means it has positive 47 in the center, but negative 47 outside of that, so they neutralize each other. It's a neutral atom. Now, what happens if we remove one of the electrons from a silver atom? We would now have 46 electrons, but we'd still have 47 protons, right? So what we would say is that the silver ion, Ag+, is the case where you have one extra proton compared to electrons, and that's why it has a positive charge. There's one extra positive charge. Now what about the lithium? The lithium atom. Well, lithium is element number 3. So a lithium atom has 3 protons and 3 electrons. If you remove one of the electrons, now you have 3 protons and 2 electrons. So you see Li plus, as opposed to Li, has 1 extra proton. That's why it has a positive charge. So when the lithium donates this electron to the silver ion, now you have a silver atom, which is neutral, and you have a lithium ion. Okay? Now, one question that sometimes people will ask was, well, can you change the number of protons? And it turns out you can, but that's not a chemical process. It requires generally enormous amounts of energy to remove protons from one another, or to remove protons from the nucleus of an atom. So we generally don't observe that in chemical processes. Okay? Now that's a redox reaction that we just looked at there. Now what I'm going to do is I'm going to show the same process using a chemical equation. Okay, so the process is silver ion reacting with lithium to form silver and lithium ion. And the reducing agent is the substance that donates electrons to the other reactant. So since the lithium lost an electron, it's called a reducing agent. And the oxidizing agent is the one that takes the electrons. So since silver had a plus charge, now on the product side it's zero charge, it's neutral. That means it gained electrons. That means it took an electron from the lithium. That's called the oxidizing agent. So the oxidizing agent takes the electrons. And the reducing agent gives the electrons. Process occurs through essentially collisions. The two reactants are close enough to each other that the electron can hop from one reactant to another. Now, one way of analyzing this is to use what are called half reactions. So I'm going to show you the example your textbook gives, just so that we can stay in line with the author. So as you read through section 4.4, you'll follow along here. So we have zinc, which is a metal solid, reacting with copper 2. And this reaction results in the oxidation of zinc and the reduction of copper. So what happened? The zinc went from zero charge, you can even put a 0 there if it's the symbol for the element, went from 0 to plus 2. That means it lost electrons. That means it gave the electrons away, so that's the reducing agent. The copper 2 became copper 0. That means it gained electrons. It became less positive, so it must have gained negative charge, which is the electrons. So that's the oxidizing agent. Now, what we're going to do is we're going to use what's called the half reactions. We're going to write half reactions here. Half reactions are a method of analysis for redox reactions. So what you do with a half reaction is you take the first element and you write it just as it is in the equation. Zinc solid as a reactant is converted to zinc aqueous plus 2 as a product. You then add electrons to the more positive side. This is more positive than that. Why? Because it has a plus 2 charge. That's positive. This doesn't have any charge at all. So the right side is more positive. It's positive, so you add electrons to that side. And I'm going to add exactly the number of electrons that it takes so that the charge on this side is equal to the charge on that side. Okay? Plus 2 and negative 2 adds up to 0. We can do a little arithmetic here. Plus 2 and negative 2, if you add those up, you get 0. So on the product side, it adds up to 0. On the reactant side, it already is 0. So we add 2 electrons to that side. If you see electrons on the product side, that's called oxidation. So what we would say, or we would claim, is that zinc got oxidized. Okay. Now let's do the other half reaction. The other half reaction is the copper. So copper 2, you just write it just like it is in the equation, and then you put the arrow, and turn it out to copper 0, copper solid. Okay, add electrons to the more positive side. The left side's more positive, so you add electrons here. When electrons are a reactant, when they're getting added to a reactant, that's called reduction. And we would say that the copper 2 was reduced in this process. Okay. Gaining electrons is reduction. and loss of electrons is oxidation. Leo goes ger, L-E-O-G-E-R. Or you can remember it as oil rig. Oxidation is loss, oil. Reduction is gain. Rig, oil rig. Okay? So this is gaining, so that's reduction. This is losing, so that's oxidation. Okay? That's called the half reaction method. We use it very often, very frequently in our analysis of redox reactions. We wouldn't use this method of analysis for precipitation reactions, nor would we generally use it for acid-base reactions. Okay? So, let me show you another example. Suppose we had this reaction, 2Ca solid, that's calcium, plus O2 gas, that's oxygen gas, that's in the atmosphere, 2CaO. Okay? Calcium and oxygen reacting to form calcium oxide. So what you do is you split it into half reactions. So let's do the calcium first. Now we have a problem. The calcium's combined with the oxide over here. What do? Think of them as ions, just like an ionic compound. +2, -2. Calcium has a charge of +2. Look in the periodic table, second column. Those elements have charges of +2. Oxygen is in column 16, so it has a charge of -2. So now you can just write 2Ca +2. Okay. I guess we don't have to put aqueous there. Oops. Okay. Now, we balance it electrical charge. The more positive side is this side, and the total charge on this side is 2 times 2 is 4. So we add 4 electrons. Okay? Now, what do we do for the oxygen? We have O2. And here it's O -2. Well, there's only one oxygen on this side, but there's 2 over here. So I put a 2 there. Now this side's more positive. This is more negative, so this side's more positive. The charge on the right side is -4, so we add 4 electrons on the reactant side. So O2 plus 4 electrons gives you 2O2 minus. Adding electrons, gaining electrons, reduction. So this is the reduction half reaction. Losing electrons is oxidation. That's over here. So this is the oxidation half reaction. Now, when an element gets oxidized, when it undergoes oxidation, it is the reducing agent. So calcium would be the reducing agent. Okay, the one that gets oxidized is the reducing agent. The one that gets reduced is the oxidizing agent. So oxygen is the oxidizing agent. Okay, so that's our half reaction analysis. Now, there are other ways to analyze. There's actually several different ways to analyze redox reactions, and the second method is through what we call oxidation numbers. Okay, oxidation numbers are a set of rules. By the way, sometimes people use the word states, oxidation states. It's an older term. So here's our rules, our oxidation numbers. We assign a number to each atom in the reaction. Okay, and that number is the oxidation number. If the oxidation number increases for an atom, meaning becomes more positive, then it's oxidized. Or oxidation is the process it undergoes. And then the reverse of that would be if the oxidation number decreases, meaning it's becoming more negative, then reduction is the process it undergoes. Okay, so for example, if calcium goes to calcium plus 2, it became more positive, so that's oxidation. If oxygen becomes O2 minus, it becomes less positive or more negative. It's decreasing its oxidation state because it's becoming more negative. So this would be reduction. Okay. So oxidation numbers. So now the way we do this is we try to keep oxidation numbers as close as we can to being like charges. So if you have an ion and it has a charge of +2, it generally the charge is equal to the oxidation state in many cases. Not always, but in many cases. So let's take a look how we do this. We just assign elements as having oxidation number of 0. So if you see NaS, that we would say the sodium has an oxidation state of 0. If you have O2, each of those atoms, this is an element. It's not a compound, because it only has one type of element. It's not an ion, doesn't have any charge, so that means it's an element. It's not a compound or an ion. So for that reason, we say it's 0. Elements are 0. Okay, so that's one rule. The next one is that if it's a compound or a polyatomic ion. So examples of polyatomic ions, H2O, that's a compound. It has 2 different elements. A polyatomic ion, PO4 minus 3, phosphate ion. 2 different elements and it has a charge. That's a polyatomic ion. Here what we do is we use a certain set of rules. Fluorine is given the number -1. That's fluorine's oxidation number. The metals, group 1 metals, lithium, sodium, potassium, rubidium, and cesium, these are given the value +1. Group 2 metals, beryllium, magnesium, calcium, strontium, barium. These ones are given the value +2. Okay. Next one, hydrogen. It's given the value +1. Oxygen. It's given the value -2. The halogens. So this would be chlorine, bromine, and iodine. These are given the value -1. These are all listed in table 4.5. Now there's one more class of substances that we should be aware of, and that's the monatomic ions. So that would be one atom that has a charge. For monatomic ions, the charge of the ion is equal to the oxidation number. So if you have a sodium ion that charge is +1, that means the oxidation number is +1. Okay? Now there are a couple exceptions for hydrogen. There are these substances called hydrides, and there it's -1. And there is for oxygen something called a peroxide. You're familiar with hydrogen peroxide, and there oxygen is -1. So those are a couple of more exotic type materials, but generally it's these rules that I've laid out here from table 4.5. Okay, so you got elements are 0. If it's a compound or polyatomic ion, you have this set of rules here, and then if it's a monatomic ion, the charge of the ion is equal to the oxidation number. Pretty straightforward. Okay. So let me show you just a couple of examples. You're going to do these in the practice problems, but let me show you. So let's assign oxidation numbers. Okay. So I'm going to do a couple that, or I'm going to do one actually that's from your textbook, KMNO4. Okay, so the way we would do this is, I'm going to follow your textbook's logic. Your textbook puts a circle underneath each element in the compound, and then they put a square, just so that you can go through the arithmetic. So the circles are where you're going to write the oxidation numbers. And then the squares are going to write where you're going to write what's called the total contribution. To charge. It's just a little way to kind of show you how to do the calculations. So let me show you how to do this one. So take the first element. The first element is potassium. Well, first of all, identify, is it a element? Is it a compound? Is it a polyatomic ion? Polyatomic ion, or is it a monatomic ion? It's got to be one of those four. Well, you look at it, it's KMNO4. It's neutral, no charge, so it's not a polyatomic ion or a monatomic ion. And it's certainly not an element. There's 3 elements in there, so it's got to be a compound. Okay, so now that we know it's a compound, we come back and we say, okay, potassium. Well, potassium, there's a rule in there. The alkali metals have oxidation numbers of +1 in compounds. And then you say, well, how many potassiums are there? There's only 1. So the total charge, the total contribution to charge would be 1 times +1. So you take the number of potassiums and multiply that by the oxidation number. Then we look at manganese, and there's no rule for manganese, so we don't know. So then we go to your oxygen. Your oxygen, the rule is it's -2. And then you ask how many oxygens are there. There are 4 of them. Each one's -2, so that would give us a total charge of -8, 4 times -2. Then you say, hey, it's a compound. If it's a compound, all the oxidation numbers have to add up to 0. So what does the manganese charge have to be for these 3 down at the bottom to add up to 0? Well, think about it. This one's +1 and this one's +8. What's this one got to be? It's got to be +7. +1 and +7 is +8. +8 and -8 adds up to 0. So this one's +7. And then you ask how many manganeses are there? There's only 1. So if the total charge is +7 and there's only 1 of them, each one has to have a charge of +7. And then these would be the oxidation numbers. Those are the numbers you report. These boxes at the bottom are just a way to kind of go through the arithmetic. But at the top, those circles, those would be the oxidation numbers. So, for example, if I had some reaction, potassium goes to KMNO4, okay, plus other reactants. Well, this has it's an element, so it has an oxidation number of 0. In KMNO4, it's +1. Well, what happened? It lost an electron, right? It became more positive, so that means that the potassium was oxidized. If for a given element, its oxidation number becomes more positive on the product side, then that means that it became oxidized. If it becomes more negative, then it underwent reduction. Okay? So that's the process of assigning oxidation numbers using these rules that are in table 4.5. Okay? Now, another form of analysis. See, redox reactions are they're all over the place. There's all kinds of different types of redox reactions, so there's different ways of analyzing these. Okay? So another thing we can look at are reactions between metals. Okay, so oxidation of metals. Okay, so for example, we could have zinc reacting with copper chloride to form zinc chloride. Boy, I wish I had a little more room here. Maybe I can work it plus copper. Okay. Okay, so there we go. So what I'm going to do is I'm going to assign oxidation numbers to everything. There's a zinc here, and then there's the total contribution. Copper, oxidation number, chlorine, oxidation number, copper, total charge, chlorine, total charge, and the same thing over here. So we're using the same analysis we just did. Okay, so here's what you can do. Go through each of them individually. The zinc on the reactant side, the zinc on the left, it's an element, right? That's just an element, so it has an oxidation number of 0. And so the total charge, of course, is going to be 0. Then you look at the copper chloride. Well, copper can actually have different charges. It could be +1 or +2. But chlorine in a compound is -1. It's group 7A. You're using those rules from the oxidation numbers. Chlorine's -1. And there's 2 of them, so the total charge is -2. Total contribution to charge is -2. So that means that the copper has to have a charge of +2 because they have to add up to 0. For a compound, there's no overall charge. So if you have -2, you also have to have +2. And then you say, okay, well, how many coppers are there? There's only 1, so that 1 copper must have a charge of +2, an oxidation state of +2. And then we do the same thing on the product side. Chlorine's -1, there's 2 of them, so that's -2, which means the zinc's got to be +2. And since there's only 1 zinc, that zinc has to be +2. And then copper over here is an element, so it's 0, and so the total contribution is 0. Okay, so now what you can do is you say, well, look what happened. Zinc went from 0 to +2. That's oxidation. And copper went from +2 to 0. That's less positive, so that's reduction. So metals will actually undergo reduction oxidation chemistry with each other. And it turns out there's a nice little sequence that shows you which metal can oxidize which other metals, which ones oxidize and which ones reduce each other. And that is shown in table 4.6. Okay, table 4.6 is on page 149, and it's what's called the activity series. So the activity series, it shows you a list of elements. And then it shows you what the half reaction looks like for oxidation. So I'm just going to pick a few of these. There's lithium. The half reaction is Li goes to Li plus an electron. That's the half reaction for oxidation. It became more positive, so it got oxidized. The one right under lithium is potassium. And then same thing, K goes to K plus an electron. Okay? So just going down, there's aluminum. Some of these metals you're familiar with, like an aluminum can. 3 electrons, right? Next one, perhaps zinc. Zinc undergoes oxidation, becomes +2, meaning it lost 2 electrons. That's really what those half reactions are showing. They're showing you what happens when the element loses some number of electrons, undergoes oxidation. You get nickel, and then you get lead. And there's lead. Okay. And then eventually you hit hydrogen. And this one's a little different. It's a non-metal, right? So sometimes people will shade this in. It's there's almost like a midpoint, as if some are above, some are below. Next one's copper. Copper goes to copper 2 and 2 electrons. Silver. And then finally gold. And then there's an order. And the order is more easily oxidized. Okay, so lithium is the most easily oxidized. Gold is the least easily oxidized. Okay, you can use this table to predict which metal will oxidize which other metal. Okay, it's a very powerful tool for that. And essentially what happens is, the higher something up is, the more likely it is to get oxidized. So lithium is the most easily oxidized. The one that's further down, for example gold, is more likely to get reduced. So if you combine lithium and gold, the gold will get reduced and the lithium will get oxidized. If you combine aluminum and copper, copper's further down, so that one will get reduced and the aluminum will get oxidized. So if they react, it'll tell you which one gets oxidized and which one gets reduced. The one further down gets reduced, the one higher up gets oxidized. We just have to be a little bit careful because there's a possibility that things are put together in such a way that nothing happens, that there is no reaction. There has to be certain requirements for these reactions to work. But again, the higher up it is, it's going to get oxidized. And the further down it is, it's going to get reduced. So let me show you an example of that. Suppose we said copper plus 2 plus aluminum. And we want to predict what's going to happen. What you would do is you'd say, okay, we're going to look and see where these metals are on the chart. Aluminum is higher than copper. So that means this one will get oxidized and this one will get reduced. So how do you figure out what it's going to turn into? Well, you just look in the chart. It tells you what the product will be for aluminum. And then for copper, it tells you essentially we're going to do the opposite. So if this one's going to get, it's lower down, so it's going to get reduced. This one's higher up, so it's going to get oxidized. The reduced form is this, Cu. So the copper turns into Cu. So it's just the opposite of what they put in. And in the aluminum, it'll get turned into Al plus 3 when it gets oxidized. So there, you're just doing the opposite. So you have aluminum, so it's going to turn into that. You have copper 2, it's going to turn into that. Okay? Now, suppose I did this. Suppose I said I have aluminum 3, and I'm going to combine that with the copper. Is there going to be a reaction? Well, you'd say, well, wait a minute. Aluminum is higher up, so it's going to get oxidized. But this is already oxidized. So aluminum cannot oxidize copper because copper is further down. So you would have no reaction here. Okay? So the one that is positive on the reactant side has to be lower down. So copper is the positive one, on the reactant side is lower down. Now, once you figure out whether a reaction is going to take place or not, the next issue is what's the balanced equation. So now you can go back and do this half reaction method. Okay, so we went over that in the beginning of the video. So half reaction method is you take the first element, so copper 2, and then you balance it. The more positive side you put the electrons. Okay, so copper 2 is more positive than copper. Again, if you need to, you can put a 0 there. Okay, so that's that one. Gaining electrons, reduction. Leo goes Gur. We're gaining electrons, that's reduction. And then you do the other one, aluminum gets converted into aluminum plus 3. I'm just reading them right off that chart, right off the equation. More positive side, so you add 3 electrons. Well, losing electrons is oxidation. But now, notice what happens. The electrons are not equal, so we're going to make them equal. We want the 3 and the 2 to match up. So here's what I'm going to do. I'm going to ask myself, what's the lowest common factor between 2 and 3? 2 times 3 is 6. So we're going to need 6 electrons. So the way we'll do that is I'll multiply the first half reaction by 3. So that'll give me 6 electrons. So now you got 6 electrons plus 3 copper 2s gives you 3 coppers. Okay, so there's that one. And then the other half reaction is the aluminum. We want to have 6 electrons for that one. So I'm going to multiply that by 2. All right, 2 times 3 is 6, so you get 2 aluminums goes to 2 Al plus 3 plus 6 electrons. And now you got that half reaction done. So those are the 2 half reactions that balance electrons. Remember, physically what's happening is the copper is ripping electrons off the aluminum. So if the copper is going to rip off 2 electrons, but the aluminum is going to have 3 ripped off, what happened to that extra electron? And the answer is, essentially what occurs is 3 coppers and 2 aluminums react. So if these are the aluminums, 2 electrons go here, 1 there, and then 2 here. So there's actually 6 electrons being transferred between the copper and the aluminum. Okay, so the copper 2 gets 2 electrons each one, and the aluminums each lose 3. So that's the, you can do all these sample problems and things like that. Now, there are some types of redox reactions that we're going to just briefly mention here. So obviously that's an important one. We just did all those problems, or all those analyses. So sometimes combination reactions are examples of redox. You may have read about combination reactions in Chapter 3. And so an example of this is N2 plus 3H2 goes to 2NH3. That combination reaction, combination because you're adding elements to make a compound, it's actually a redox reaction. And the reason we know it's a redox reaction is that elements have oxidation numbers of 0. So nitrogen and hydrogen are 0. But in compounds, the oxidation numbers have to add up to 0. So you've got nitrogen and hydrogen, right? Well, hydrogen is plus 1. The total contribution, there's 3 of them, so that's plus 3. So that means the nitrogen has to be minus 3. So what happened? Nitrogen went from 0 to minus 3. That's reduction. So that means nitrogen is the oxidizing agent. And then hydrogen went from 0 to plus 1. That means it lost electrons, so that's oxidation. So sometimes it's the case that combination reactions are redox reactions. There's also decomposition. Decomposition reactions are often redox reactions. So an example of this would be, let's do KClO3. So 2KClO3 goes to 2KCl plus 3O2, just balancing the equation. So here we have 3 elements. Here we have 2 elements. And then here we only have 1 element. Elements are 0. If elements are 0, so oxygen is 0. We already know that one. Now we have compounds. So I'm going to work from right to left. Potassium is alkali metal. Chlorine is group 7A. So this is plus 1 and minus 1. And then we come over here. Potassium's plus 1. That's an alkali metal. Chlorine, well, it's not so clear what happens here. Oxygen's minus 2. So there's 3 oxygens, so that's minus 6. There's 1 potassium, so that's plus 1. We're ignoring the coefficient. We're just dealing with the one molecule of the substance. Okay, so plus 1 and minus 6, that's minus 5. So that means the chlorine's got to be plus 5. Okay, so decomposition, compound getting converted into smaller things, into simpler products. Look what happened. The chlorine went from plus 5 to minus 1 on the product side. Oxygen went from minus 2 to 0. Okay, so this is oxidation. It became more positive, less negative. This one became more negative, so this is reduction. Okay, so decomposition reactions. And then finally, we also have combustion reactions. Combustion reactions are most certainly redox reactions, for sure. So the example they give in your book is the combustion of methane, CH4, plus oxygen, becomes CO2, carbon dioxide, and then 2 waters. Okay, so there we go. Methane plus oxygen, carbon dioxide, water. Well, there's 2 elements here. There's only 1 element here. Oops. 2 elements there. And then 2 elements here, water. Okay, so it doesn't matter which one you do first. Elements are easy, so oxygen is 0. Come over here to carbon and hydrogen. Well, there's no rule for carbon, but the rule for hydrogen is plus 1. There's 4 of them, that's plus 4, so that means the negative's got to be minus 4, which means that the carbon is minus 4. There's only 1 carbon there. Product side, carbon dioxide. Well, oxygen's minus 2. Sorry, a little messy there. 2 oxygens, so that's minus 4. That means the carbon's got to be plus 4. Water, hydrogen is plus 1, oxygen is minus 2. There's 1 oxygen, so that's minus 2. There's 2 hydrogens, that's plus 2. Compounds add up to 0. So look what happened. The carbon went from minus 4 to plus 4. I realize it's hard to see that plus 4. So what happened? It lost electrons. Actually, it was 8 electrons. That's oxidation, a lot of electrons. And then the oxygen here on the reactant side was minus 2, and it became oxygen, I'm sorry, not minus 2, 0. It's an element, right? So the oxidation number of the element was 0. And then on the product side, it became negative 2 every time. So oxygen minus 2. Well, that means it gained electrons, so the electrons are over here on this side. Now, why is there 8 here and why is there 2 there? Well, keep in mind that, in fact, there's 4 oxygens on the product side. 2 here plus another 2 there. So it's really 4 of these and 4 of these. So it's 8 electrons. So 8 electrons here, 8 electrons there. Okay? So this is reduction. Oxygen is the oxidizing agent, and carbon is the reducing agent. Okay, so that's a redox reaction also. And one thing to mention, there's a little chart here at the end of the section, and this chart is figure 4.8. And I recommend looking at that. That's on page 153. It shows you the common oxidation numbers for different elements. So for example, hydrogen is plus 1, but it can also be minus 1. Okay. Notice that for lithium, there's only 1 common oxidation state, and that's plus 1. And the same is true for sodium. Sorry, this is 3. And the same is true for potassium. So some elements are very regular in terms of their oxidation numbers, lithium, sodium, and potassium. But when you look at some of the transition metals, you get more variation. So for example, element number 23, which is vanadium, it actually has multiple oxidation numbers. One possibility is plus 5. Another possibility is +4. Another possibility is +3, and another possibility is +2. What happens when you get to the next element over here? Chromium. Chromium can actually be +6, +5, +4, +3, +2. So the transition metals, they have quite a bit of variation in terms of their oxidation numbers. They're not so straightforward. Vanadium could have one of many different oxidation states, as could chromium. The alkali metals, much more predictable, +1 for the alkali metals. Okay, so that's a nice little table to take a look at. And there you go. That's our introduction to oxidation reduction reactions, or redox reactions.